Hi all, this is Mr. Yeager for Honors Chemistry, and we are finishing up our unit on chemical reactions with the redox reactions. All right, and so these guys can be a little bit tough. You got to just really be careful going through the steps of redox. But let's first figure out what does it mean to do a redox reaction. So redox is short for a reduction oxidation reaction. Okay. And so what's happening here is there's actually a change of charge that will occur between two elements, because essentially electrons are being transferred from one element to another element. So I briefly mentioned that, I believe, back in like types of reactions or predicting products, that we just will assume that the charge will remain the same for those metals as they go from one side to the other side in your predictions. Okay. The thing is, in a lot of these cases, especially with double replacement reactions, but also with single replacement or any other types that we have where they're rearranging, we can have the charges of the atoms change as the electrons are transferred between the elements. So we call this reduction or oxidation. Oxidation occurs when the charge of the atom is going up. Okay, in other words, the element is becoming more positive. It is being oxidized when the charge is going up. Reduction, clearly that one's the idea is it's being reduced. The charge of the atom's going down. So I mean, if you happen to be like, I don't remember what oxidation means, well, hopefully you know what reduction means. It means to reduce. So it's going to become more negatively charged. Now again, you got to be careful with this, because I mean, we might have situations where you might have an atom go from, Cu plus to Cu3 plus. We should see that clearly, that hey, it's being oxidized. The charge of it is going up. Okay. I guess one that might be a little more confusing would be something like, maybe you have the charge of I don't know, we could say like N is -3 and then N is -1. This is being oxidized because the charge is going up. It's becoming less negative. So that's where, again, maybe just being a little careful, especially with those negative numbers. But charge up, oxidation; charge down, reduction. And again, they go together. One is going up because it's giving away electrons. The other one's going down because it's accepting those electrons. Okay. So here's just a quick little picture showing that. I don't know why they spell reduction as D-U-K. All right, but oxidation reduction, what you have there basically is, at the beginning here, you have sodium is 0 charge. This chlorine is 0 charge. I don't know why it wouldn't be Cl2. It should be Cl2. I'm going to put that there. All right, and so what we have there is basically, we can see that they are changing their charges. Sodium is being oxidized, chlorine will be reduced. And again, you're seeing that down below as well when it is written more correctly. Okay, so it's kind of double of the same one there. All right, so that's what's going on. And again, it's occurring because the sodium's giving away its electron to the chlorine. Okay, all right. A couple things though. First, we have to talk about oxidation number, oxidation states. All right. Because in the end, you're going to be looking at a couple different elements. You might be going, wait a minute, which element is changing charge? Well, a lot of elements keep their charges, and that's what we want to try to make sure we understand. All group 1 elements will keep their +1 charge, no exceptions. So if you see an element from group 1, Li, Na, K, etc., it'll always be +1. It's probably the other element that's changing. Group 2 will keep its charge, +2. Hydrogen pretty much will always be +1. There is the exception that it could be a hydride and combined to a metal. That, again, I don't think we're going to run into too much, but if we do, I think we'll notice it. It'll be with like NaH, and since Na can't be anything but +1, H must be -1. Okay. The fluorine is always -1. Oxygen, guys, is pretty much always -2. It does show there that if it's hydrogen peroxide, it'd be -1. I don't plan on giving you anything with hydrogen peroxide or peroxide involved. Chlorine is pretty much always -1, but you will see if it's bonded with like another halogen or a fluorine or oxygen, it could possibly take on another charge, but in general it'll be -1. All the others then, all the other elements, and I'm going to show you down, we're going to do a little bit of practice in a moment, basically we have to find their charge. The last little rule to pay attention to, and you saw me do it on the first example, is if it's a lone element basically like it's just by itself, like sodium was by itself. Or if it's a diatomic, like chlorine was above, they have zero charge. All right? So that's where we had the oxidation reduction between sodium and chlorine, because they both were initially zero, and then they became charged. One went up, one went down. Okay? So lone elements are always zero. But again, just to hit these, oxygen guys pretty much take that as -2. Hydrogen pretty much always +1. There's no real questions about group 1 and group 2. And in general, any halogens is -1 unless you start sitting there and going, wait, it's bonded with oxygen. How can I try to figure this out in some cases? I think what you might run into is it's kind of weird because it's the idea of what charge could it possibly take? And it might be in the form of a covalent compound. So we'd actually, even though covalents don't have charge, we're going to look at it as if they might have some charge to it. Okay, it's almost like a, I don't want to call it, well, let's just call it oxidation state. Okay, so let's practice some of these. So you see I have NO right here. NO. Well, the idea is O is -2. This whole compound has to come out to 0, so that means this nitrogen must be +2. There you go. The nitrogen is +2. I know it's already throwing you off. You say, wait a minute, I thought you said nitrogen is always -3. That's where we're starting to kind of break some of these rules a little bit, that they could possibly take some other charges with them. Okay? NO3 minus. NO3 minus. So I got NO3 minus. So the idea is the overall charge of this is -1. Well, oxygen is -2 times 3 is -6. So what plus -6 will give me -1? This nitrogen has a +5 charge. So that would be the oxidation state of the nitrogen in nitrate. Let's do the next one. Basically solving for the manganese, the charge of the manganese. So I got MnO4 minus, so the overall charge has to come out to -1 because it's a polyatomic. I got 4 oxygens, so 4 times -2 is -8. So X plus -8 equals -1. This manganese must be +7. All right. It's sort of what you had to do a little bit when you're figuring out the charge of a transition metal when we were doing ionic compounds. The last one down at the bottom, I got HSO4. What I'm trying to figure out is the S. So I have HSO4 minus. So again, the overall charge comes out to -1. -2 times 4 will be -8 from the oxygens. I'm looking for S, and the hydrogen, because it's not with a metal, is +1. So basically I got X plus -7 equals -1. All right, is that right? Yep. And so this has to be +6. +6. The sulfur is +6. 1 plus 6 is 7, minus 8 is -1, if you want to go back and look at it that way. So that is an initial step we're going to have to take, is trying to figure out the charges. That'll be part of your questions before we get into actually writing the redox reaction completely. All right, so moving on. The second thing I'm going to be asking you to do is you need to identify the oxidizing and reducing agents. I say this is confusing because the agent is the opposite of what it's doing, like what itself is doing it to itself, like what's happening to that element itself. So you can see here, the oxidizing agent is the atom that will take the electrons, because the idea is it's going to oxidize the other atom. It's going to increase the charge of the other atom. So that means it's taking electrons and will actually be reduced. So again, this is one of those kind of tricky things that some people find different ways to do it. You can sit there and go which one's reduced, which one's oxidized, and then you reverse and tell me which agent it is. So the atom being reduced is the oxidizing agent. It is the one causing the other atom to be a higher charge. Vice versa, the reducing agent, it's the one that's giving electrons away because it's going to make the other atom more negative. This is the atom being oxidized. So if I do that initial reaction where you had Na plus Cl2 produces, and I know this technically is 2, we're going to do it this way, 2Na plus 2Cl minus, okay? What we have here is, again, sodium is getting oxidized. That means sodium must be the reducing agent. chlorine is being reduced, so therefore it must be the oxidizing agent. Again, once you recognize one, you know the other one must be the opposite. All right? So that's where, again, we're trying to play around with this, and I know that can be very confusing. So here's another example. Mn plus 2 goes to Mn plus 7. Its charge is increasing, which means it's oxidized, which means it must act as a reducing agent when it's, in this case, with something like NO3 minus. NO3 minus goes from NO3 minus to NO. We kind of just did that one. Nitrogen went from plus 5 to plus 2, so charge decreased. It got reduced, which means it must be the oxidizing agent. And again, we're looking at the initial reactants. That is, the reactants are the oxidizing and reducing agents involved. So finally, the last thing we got to is to balance, write and balance redox reactions. Write and balance redox reactions. This can be a bit, and you got to be very careful going through this. You know, it does depend on whether you have an acidic or basic solution. In the end, basic has an extra step to it. Basically, we do the same thing for both acidic and basic up to a certain step. All right, so I'm breaking this down quite a bit. It looks like a lot of steps. You got to be really careful with your counting. You got to be really careful with your balancing. All right, this is something that can be very frustrating if you keep making mistakes with it. So you can take a quick look here. I don't feel like I need to read everything out. I'll kind of say it out loud as I go through it. If you want to pause for a second to write these down, you can see the steps through both of them. Okay, essentially, you know, up to essentially like the first 5 steps are the same for both of them. Okay, the first 5 steps. Steps 6 and 7 is kind of what you're doing, and well, actually, yeah. See, that's where we are starting switching it a little bit. But we have to then add the reactions together. Beyond that, after you add the reactions, then you have that extra step with the basic solution where you add these hydroxides to both sides of the reaction. So I'm going to go through one of each of these so you can kind of see how this would all work. Okay? And I'm going to show you how the problems are that we're going to be doing in my class. So let's say I have a reaction here where it's I2 plus OCl minus produces IO3 minus plus Cl minus. Okay, and so what I'm asking you to do here is we're going to do 3 things. Okay, I'm going to say I want to know the charges, the charge change. Okay, I don't usually call it that. Let's just say I want to know the charges of the reactants into products. I want to know how the charges are changing. Okay, so that would be step number 1. 2, I want to know what is the reducing agent and the oxidizing agent. And then I want to balance the redox reaction. All right, so here we go. What fun. So the first thing to do is, and we probably want to do this step, so we're kind of doing the first step of the balance the redox reaction. The first step is, it said, write the half reactions. What that means is write the reactions of the elements from the reactants to the products that basically look like they're the same, like there's a similarity between the two, where you have that other than H and O element, put those together, and we're going to separate out this full reaction into 2 what are called half reactions. So we have I2 is going to become IO3 minus, and then OCl minus becomes Cl minus. So those are my half reactions. I do that because now I can identify the charges involved. So I2 is a diatomic by itself, a lone element, so it has a charge of 0. But over here I have IO3 minus. So this means we have to do that charge stuff again. -1. Oxygen would be 2 times negative 2 times 3. I'm kind of doing that backwards, so -6. So what plus -6 is -1? That would be +5. Which again, you're going, what? You know, how is that happening? But that's what we got with it. Okay, this iodate ion actually has a +5 charge. It's actually because it gives up all its p electrons. Okay, so iodine is going from 0 to positive 5 charge. All right, you can already kind of tell which agent it's going to be, but let's do the other one just to be clear. Down here, O is always minus 2, okay? And so over here, with the overall charge is minus 1. Well, we got minus 2 plus what equals negative 1. This must mean that this chlorine is actually a positive 1 charge. And then over on the other side, that's kind of easy. It's a negative 1 charge. So chlorine's going from positive 1 to negative 1. So we did the first part. We figured out the charges of the elements that are changing and how they're changing to what. So iodine up top here is going from 0 to positive 5, which means it's being oxidized, which means it's the reducing agent, because it's the opposite agent of what happens to itself. It's being oxidized, so that means it's trying to reduce chlorine, which is what's happening. Chlorine is getting reduced, so therefore chlorine is the oxidizing agent. Okay? So that's what we do kind of at the beginning of every single redox reaction. All right, so let's move on. So let's go with this. We have, I'm going to rewrite the reaction. I2 plus OCl minus produces, IO3 minus plus Cl minus. Okay? All right, and you can clearly see this is not a balanced equation, and we got to figure out what to do with it. So we got to do our two half reactions. Okay? We got I2. I'm going to try to put this on two sides, see if I can fit it all. Sorry. I2 yields IO3. Step number 1, write our two half reactions. OCl minus minus yield arrow Cl minus. I can do this. Okay, see, I'm already getting intimidated. All right, so first step, take one at a time. Don't do these together. It said this is in an acidic solution, so I'm following the acidic steps if you wrote all those down. Step number 1, balance any atoms that aren't hydrogen or oxygen. So I have 2 iodines, I have 1, I'm going to put a 2 right there. Step 2, add waters to balance out the oxygens that you see. So I have 3 oxygens on the right, which means I will need 3 waters on the left, because 3 oxygens, 3 oxygens. Next step, balance the hydrogens by adding hydrogen ions, H+. Well, I have 6 hydrogens now from this water, so this is going to be plus 6H+. Then, after that, balance the overall charge on both sides by adding in electrons to get the charge equal. Well, the thing is, on the left-hand side, the charge is simply 0. Okay? On the right-hand side, the charge is positive 4. Okay? Positive 4. All right? Yep, positive 4. Is that right? Trying to make sure I'm doing these up. See? This is good that you get to see this. I made a little mistake. You probably are sitting there going, Mr. Yeager, stop. Let me go back. I2 produces IO3. I put a 2 here. I said there's only 3 oxygens. There's 6 oxygens. So this is 6H2O. And then over here, it's going to be 12H+. Sorry, that's minus right there. Okay? So on this one, I need to be a little bit more careful. There you go. Lesson on being very, very careful and counting nicely. The charge is still 0, but on this side it's plus 10. So I actually need to add 10 electrons to this side of the equation. Okay, 10 electrons. For the O's, I stopped there. Okay, that's basically one half reaction. Go to the other side now. Chlorines are the same, so I'm good there. I have 1 oxygen, so I'm going to add 1 H2O. Let me double check, 1O, 1O. I made that mistake last time. Then I have 2 hydrogens, so I'm going to add 2 hydrogens to this left side. And then I have a positive 1 charge on this side, on the left side, on the reactant side, and a negative 1 charge on the product side. So for this, I need to even out these charges. I have to add electrons. I'm going to add 2 electrons to the left-hand side. All right? So there. I have now balanced out the charge. If I double check, that's 2 electrons plus 2H+ is 0, and then negative 1, and then negative 1 on the other side. What we then do is we do what I call, we scale the two. What we need to do is we need to have the number of electrons in both reactions be the same, and you got to basically multiply by a whole number, either one reaction or both, to make them be the same number of electrons. What that means is I'm multiplying this whole OCl minus half reaction times 5. And so this will come out to 10 electrons plus 2H plus. Oh, see, got to multiply that 5. 10H plus 5 OCl minus plus yields 5 Cl minus plus 5 H2O. All right, and so that's where we get our balanced electron reactions. We scaled it. All right. Now what we do is we add the two reactions together completely. So put everything that's reactants on one side and everything of products on the other. So I get 6H2O plus I2 plus, that's all I have on that one. I need to grab everything on the other reaction. 10 electrons. I'm grabbing all of this. Plus 10H plus 5OCl minus will produce, go back to my first reaction, 2IO3 minus plus 12H plus 10 electrons plus my last two things here, 5Cl minus plus 5H2Os. What I now do is I cancel everything out on opposite sides that's the same, all right? Or I reduce one side or the other based on how many are on the other side. So basically what I mean is, for every water on the left, I cancel out a water on the right. For every I2 on the left, I cancel I2 out on the right. Now I don't have that. But basically we're looking at the waters, the electrons, and the hydrogens and see what happens. Everything else will just kind of come along with it. So if I take this piece by piece, I have 6 waters on the left, I have 5 waters in the products. So I'm going to eliminate all 5 waters, and that means I only have 1 water left on the left side. The electrons, they should cancel out. We should not have any electrons in our final reaction. So electrons, 10 electrons, 10 electrons. Hydrogen ions, I have 10 on the left, and I have 12 in the product side. So all 10 of these go away, and I'm down to 2 hydrogen ions on the right-hand side. Once I have that done, I bring everything that's left over. So H2O plus I2 plus 5OCl minus will produce 2IO3 minus plus 2H plus 5Cl minus. And then you pray that everything is balanced, including charge. So we double check that. I have 2 hydrogens. I have 2 hydrogens. I have 1 plus 5 oxygens, so that's 6. 2 times 3 is 6. I have 2 iodines, I have 2 iodines. I have 5 Cls, I have 5 Cls. Atoms look good, let's hope the charge is all good. All I have over here is 5 OCl minus, so I have a negative 5 charge on this side. I have a negative 2 charge plus positive 2 charge, which basically cancels each other out, plus a negative 5 charge. Yay, yay, yay. I am balanced on both sides of the reaction. Yay, yay, yay. That's what we're looking for. All right, so let's do one more, but now we're doing it under basic conditions. So for the basic conditions, let's get my reaction here first. I have PbOH4 minus 2 plus ClO minus, so it's going to kind of look similar, forming PbO2 plus Cl minus. Okay, so for this, what I got to do, let's do what I did first. Okay, let's do my half reactions. I'm going to try to speed this up just a little bit. PbO2. Okay, on the other side, ClO minus produces Cl minus. All right, if I look at it, I'm changing the Pb. Okay, so I'm changing the Pb's involved with both of these. Based on what I can figure this out looking at these things, okay? OH minus, that's hydroxide. They have a negative 1 charge times 4. Again, trying to come out to negative 2. This is negative 4. So this Pb is plus 2. Over here, oxygen is minus 2 times 2. So this is negative 4. So this must be positive 4. So my my lead is going from plus 2 to Pb plus 4. All right, so it's being oxidized, which means it must be the reducing agent. Over on the other side, I got the same as what we did before. So this would be Cl plus 1 going to Cl minus 1, so it's being reduced, so it's the oxidizing agent. Okay, so that's that part. All right, let's get to balancing. All right, the beginning of this looks all the same. Okay, we're going to try to do the exact same thing we've already done. Let me erase all this extra stuff around it. Okay, all right, and let's try to get going with this. So, first thing, balance the like elements, or the PBs. They're both the same, so we're good there. Now I got to balance H2O. I got 4 oxygens on this side, 2 oxygens on the other side, so I need 2 H2O right here. Okay. At that point, I balance my hydrogens, but they're already balanced, 4 and 4. Oh, sorry, this is minus 2 right here. I need that charge. Okay. So what this is showing me is I don't have to add any hydrogen pluses, but I still need to balance out the charge. I still do that last step, and I'm going to add 2 electrons on this side. Okay. ClO minus, same thing. Cl's are good. Add an H2O on this side to balance out the oxygens. Now I balance 2 H pluses on this side. That gives me positive 1 versus negative 1. And guess what? I got 2 electrons. So yay. This is overall looking really, really nice because guess what? My next step would be to scale, but I have the same number of electrons in both of my half reactions. So I'm going to add them together now. I'm going to add them all together. So I get PbOH4 minus 2 plus 2H plus 2 electrons plus ClO minus produces, I kind of didn't give myself much space here, PbO2 plus, I actually add these H2Os. I know they're on the same side, that's kind of weird, but we add those, 3H2O and then plus 2 electrons. All right, I do cancel out anything I can cancel out my 2 electrons. Okay. Then what I do is, this is the extra step in base. What I have to do is I have to add hydroxides, OH minuses, to cancel out, not cancel out, but to add to any H pluses in the problem. And however many I add on the one side, I have to do the other. So since I have 2 H pluses here, I'm going to add 2 OH minuses, which means I have to add 2 OH minuses to the other side. What happens now is these, the H plus and OH minus, they're going to form water. So I have now 2 H2Os on this side. So let's look at it now. PbOH4 minus 2 plus 2 H2O. So again, try to quickly review that. I didn't mean to go too fast. You balance out any H pluses you have with any OH minuses. So since I have 2 H pluses, I get 2 OH minuses, and I add that to the opposite side as well. The H plus and OH minus will form water. So there we go. ClO minus produces PbO2 plus 3H2O plus 2OH minus. Okay? The thing is, I do then cancel out anything that's still the same on both sides. So I do have 2 H2Os, so I'm going to get rid of that. And I'm going to get rid of 2 of these, so I'm left with 1. And then I am left with PbOH4 minus 2 plus ClO minus produces Cl minus plus H2O. Oh, things disappearing on me. Cl minus plus H2O plus 2OH minus plus PbO2. Let's double check. 1 Pb, 1 Pb. I have 5 oxygens. 4 plus 1 is 5. 1, 2, 3, 4, 5. 4 hydrogens. I have, 4 hydrogens. 2 plus 2, 4 hydrogens. 1 Cl, 1 Cl. Let's look at the charge. I'm minus 3 on this side. I am minus 1, minus 2, minus 3. I have 2 of these right here. Minus 3 on this side. We have done it. So that is the whole process. All right, it is intense, it is frustrating at times, you miss things. You saw me miss, again, one of the early steps, which is counting the oxygens. It's going to be something that's going to take a lot of trial and error to get all correct. If you need additional help, I did add in, again, Bozeman's science here. Again, they do it very, very well, very clearly if you want to kind of go through and check that out at all. But that is it. All right, thank you very much. Have a good one.